thank you, Wendy, and thank you all for showing up. Wendy wanted something that would draw an audience, so I came up with this title, and it is a little bit over the top. What I'm actually going to do is I'm going to spend about half of the talk talking about natural history of Mount Rainier, and then we will segue gradually into hazards towards the end of the thing. So it won't be, if it was all about hazards, it would be kind of a downer by the time we were done. So, Mount Rainier, America's most threatening volcano, and how this affects residents of the Pacific Northwest. First off, why is Mount Rainier here? This is a physiographic map of the Pacific Northwest, Seattle, Tacoma, and so forth, including the offshore region. And you'll notice some features, these long ridge-like regions in the offshore region, there and there, some sort of rumpling along here where it's smooth to the west and more uplifted and irregular to the east. The volcanoes of the Cascade Arc, I'll call it an arc, exist because of a process known as subduction. Oceanic crust forms along a series of spreading ridges in the offshore region, creating what's known as the Juan de Fuca Plate. This Juan de Fuca Plate moves towards North America in this direction at about 4 centimeters per year. That oceanic plate, in total, is denser as it cools than the mantle that lies beneath it. And so it eventually falls back down into the mantle. It falls back down into the mantle along this boundary, which is known as the subduction zone. At the southern end of the subduction zone, it ends by joining up with the San Andreas Fault. At the northern end, it joins a series of similar faults that lie to the west of Vancouver Island. But one of the consequences of that subduction is the creation of a volcanic arc. So each one of these colored diamonds represents one of the major volcanic centers. This is Lassen Peak, Shasta, Crater Lake, Three Sisters, Jefferson Hood, and so on, including Mount Rainier there. And then there are also some somewhat different volcanic centers that lie to the east of the volcanic arc. So in very simple terms, this is why Mount Rainier and the other Cascade volcanoes exist. Well, Mount Rainier towers over the southern Puget Sound region. There are about 2.5 million people who live or work within sight of this volcano. How did it get to be this way? What sorts of hazards does it pose for the region? Those are the sorts of things that I'm going to be summarizing. But first, before I even get to that, I want to make the point that it's not the first volcano that was present in that location. This is a map, so Mount Rainier is here, and those are its glaciers. And you'll see some points with some numbers, and these colored areas here and here. These are ages of volcanic rocks that we've sampled from deposits of lahars. Well, what is that word? Lahar is an Indonesian word for a volcanic mud flow. And we're not talking about little volcanic mud flows, or little mud flows, the sort of thing that might, say, slump and close a portion of the freeway. We're talking about things that are capable of traveling tens of miles. So these ages, MYR, that's million years ago. So there are volcanic rocks in these deposits which were shed from the location of Mount Rainier that were on the order of 1 million years old. So this is evidence that there was an earlier volcano where Mount Rainier sits now, and there are some little pieces of it that are left, such as off on the east side at a place known as Panhandle Gap. So there was an earlier volcano, and it shut down and was largely eroded away. And then Mount Rainier itself grew in that location on the remnants of the earlier edifice. And this is what much of Mount Rainier looks like. We're standing on the upper Carbon Glacier, a cliff known, so this is the north side of Mount Rainier. This is a cliff known as the Willis Wall. This is a ridge known as Liberty Ridge. To give you a sense of scale, this picture was taken at about 9,000 feet elevation, and these ice cliffs are at about 13,000 feet elevation. So there's about 4,000 feet of relief in this photograph. So El Capitan in Yosemite, which is about 3,000 feet, would get up to about there. So quite big exposures. Okay, what you'll also notice is that there's a stair-stepped appearance to this, where there's a cliff band and a rubble slope and a cliff band and a rubble slope, and repeated again and again and again. Well, each one of these doublets of cliff band and rubble slope is an old frozen lava flow that erosion has eaten into so that we can see it in cross-section. So lava flow, lava flow, lava flow. And to give you a sense of scale on these things would be on the order of, say, 25 to 100 feet thick, varying from one to the next. Now, these rubble slopes erode quite easily. So if they are preserved between the flows, and the flows are generally parallel to one another, that's telling us that not much time has passed between eruption of one lava flow and the next. If you look carefully, you can see a few places, such as here, where the rubble has been cut out. But this succession of lava flows is, as the geologists call it, largely conformable, tells us that the lavas came out one after the next in rapid succession. In other words, at times, when Mount Rainier has wanted to erupt, it's done it again and again and again and again and again. How long might these sorts of things take? I'll get to that later in the talk. This is another photograph. This is up near the summit of Mount Rainier, and again, we're looking at lava flows. So this is the dense interior of the flow, and it forms these cliffs because the interior cools slowly, so the rock has the ability to harden up into a single mass, whereas the tops of the flows are rubbly, and that's because the upper portion of the flow is exposed to the air and rain and snow, and as the magma is moving its way, magma is a technical word for molten rock, as it moves down the hill, the top of the flow gets jostled and broken up. That's why they have rubbly tops. Well, what you can also see between these lava flows is a small region of lighter colored material. That's volcanic ash, and it's produced by explosions that take place between the eruptions of the individual lava flows. So even though one flow is coming out, and in a short period of time after that, another flow came out, and in a short period of time between that, another flow came out, there were also explosions that were taking place between those events, and probably during them as well. So here's a nice space shuttle photograph of Mount Rainier, and you can see the glaciers and you can see the drainages radiating away from the volcano. And then we can drape on top of that the geologic map of the volcano. And you'll see that I've divided so these various colored units, colored areas, represent rocks from Mount Rainier of different ages. And here I've shown the age categories, and Ka stands for kilo annum, or thousands of years ago. So for example, this color is rocks that are more than 500,000 years old, 420 to 500,000 years old, and so on. And we determine these ages by radiometric dating methods, mainly the potassium-argon system or the argon-4039 system. But what I want to focus on at the moment is that the various large lava flows, if you look carefully, you see that they're actually sitting up on the ridges. So this one, for example, this is Rampart Ridge, appropriately named, and there are valleys on either side of it. And this is seen again, for example, this is St. Andrews Park, Colonnade Ridge in this area here, and so forth around the volcano. It's unusual that the lava should be sitting up on tops of the ridges as opposed to down in the bottoms of the valleys. I mean, lava behaves like a fluid. You would think that it ought to be sitting down in the valley bottoms. Well, that it was sitting up on the ridges. Now, I think I have another photograph. So this is a photograph from up on the west or Mowich face of Mount Rainier, looking down towards lower Sunset Ridge. And this is all a lava flow that makes that ridge, and then there's a deep valley on one side and a deep valley on the other. The early workers at Mount Rainier saw this, and they thought that what was going on was that these large ridge-forming lava flows were very old, and that they had originally flowed down ancient river valleys and displaced the rivers to either side, and then those rivers had whittled away at the adjacent country rocks and left the lava flows sitting up high on the ridge crests, flanked by deep valleys. Well, when we started dating these lava flows, we found that many of them were vastly too young for that kind of process to have taken place. They would be, say, a few tens of thousands of years old. And if erosion was capable of whittling away rocks that quickly, there would be no volcano here at all. So there's something else has to have been going on to explain why the large lava flows at Ranier create ridges as opposed to filling the valleys. And some of the evidence that we started to see for what might be going on is shown here. There's a person standing at the bottom of this cliff. This is a large lava flow on the west. This is the known as the dacite, which is a kind of lava of Emerald Ridge. And normally the large lava flows have vertical columns passing up through them, but every so often along their sides we would see these horizontally oriented columns. Now columns form, they point in the direction of maximum cooling. They're like, well, they're sort of like, well, they're that. They point in the direction of maximum cooling. And the width of a column scales with the rate of cooling. So a little column cooled fast, and a big column cooled slowly. And you'll see that these are little columns, and they're pointing out the side of this lava flow. And there's a valley here off to the side. It's about 600 feet down to the bottom of the valley. So what this sort of relationship is telling us is that there was something in this area where these trees now stand that was very cold when this lava erupted. And the lava banked up against it and chilled against it. It's not a fissure. And if we go to areas where lavas are erupting into ice, we start to understand what happened. This is Veniaminoff volcano. It's another volcano that I've worked on. I didn't take this picture. Betsy Yunt took it back in the 1980s when Veniaminoff was erupting. So there's a cinder cone here, and this is a lava flow that's come out from that cinder cone, and it's melted into the ice, thick ice, that's filling a caldera. And you'll notice that it's ponding. In other words, when the lava comes out and it touches the ice, it chills against it. And it essentially builds its own dam and then fills up behind that dam. If this was this is pretty flat, so the lava is just sitting at the base of the cinder cone. If this was on a steeper slope, that lava would move downhill, bounded on its side by walls of ice. And it might, at Ranier, look something like this. Now this is Four-Peaked volcano, and Four-Peaked has a degassing event taking place as we speak. So far we have no evidence that lava has actually come out underneath the ice at Four-Peaked, but there are places, such as in Chile, that are not well photographed, where lava has come out and it actually tunnels underneath the ice, or melts a little trough or channel through the ice, bounded on either side by ice walls. In other words, the ice has the ability of controlling where the lava goes. And this, in part, helps to explain why there are ridge-forming lavas at Ranier. The sort of model that we've put forward is that during the Ice Ages, the Pleistocene, the valleys surrounding Mount Rainier were filled with hundreds to over 1,000 feet thick ice, big valley-filling glaciers. So when the volcano starts to erupt, lava pours down the side of the volcano, and if it runs into ice, it chills against it, and that steers the lava. The lava can't melt all the way through that ice, so it would, for example, in this area, flow down at the boundary between ice and exposed rock, where similarly here it would flow down between the boundary between ice and exposed rock. And eventually, moving away from the volcano, the ridges descend beneath the level of the ice, and the lava can actually continue in those directions. Well, where are they going to continue the furthest? They're going to continue the furthest where the ice is thinnest. That's where the ice provides the least barrier to further advancement of the flow. Whereas where the ice is thick, the flow just doesn't have enough heat in it to move in those directions. Well, at the end of the ice ages, the glaciers melt back, and we're left with deep, open valleys, much smaller glaciers, and lava flows that are capping the ridges. And this is how Mount Rainier came to be surrounded by ridge-forming lava flows that radiate from the volcano much like spokes of a wheel. It's not reverse topography. So when you go to Mount Rainier next, and you're looking around and you're seeing these big ridges with their columnar joints, they're made up of lava, put your Ice Age glasses on and start imagining what this place was like 20,000 years ago, 200,000 years ago, when most of the surrounding region was buried beneath thick glaciers. Well, so what are some of the other things that volcanoes can do? They can produce pyroclastic flows. This is a photograph that one of my colleagues from the Geological Survey, Chris Newhall, took of a pyroclastic flow coming down Mayon volcano in the Philippines. Well, what is a pyroclastic flow? Well, you can see there's a lot of dirt in the air there. It's a fast-moving avalanche of volcanic rock fragments, usually so hot that they're still incandescent, and at times have the ability to stick back together when the material comes to rest. They can move at 100 kilometers an hour and sweep across large areas. They're of significance, they would be of significance at Mount Rainier because they tend to be erosive of ice. This has been observed at, for example, eruptions of Redoubt volcano in the 1990s in Alaska, where pyroclastic flows swept out onto a glacier, entrained the glacial ice and snow, and that liquefied the pyroclastic flow, turning it into a lahar that was able to travel down to Cook Inlet, close to an oil facility. Fortunately, nothing happened to the oil facility. So if there were pyroclastic flows erupted at Mount Rainier, this would be one way of producing lahars very rapidly from the volcano. Well, do we see evidence of this? Well, I wouldn't have done all this leading up to it if we didn't. This is a cliff, for example, on the flank of Little Tahoma. It's a spur peak from Mount Rainier, and these very blocky material that you can see that are somewhat layered and bedded are deposits from hot pyroclastic flows that cascaded down the side of the volcano. So there's some evidence that the volcano erupts pyroclastic flows. And then in other areas, as I said before, where a pyroclastic flow comes to rest and it's still hot, the material can stick back together again. This is a process known as welding, and it produces something that looks like a lava flow. And this is in the headwaters of Couts Creek. This is Pearl Falls, and Pearl Falls is cutting down through what has been named basalt cliff. In fact, it's not basalt. It's what we call a welded pyroclastic flow. This phenomenon of the hot material sticking together is called welding. So pyroclastic flows, lava flows. Well, what else do volcanoes do? Well, this, of course, isn't Mount Rainier. This is Mount St Helens, May 18th, 1980. This is a photograph taken by Austin Post of the Geological Survey. Mount Rainier, of course, also produces tephras, but it's not very good at it. This is about as big as they get. This is Eric Bard. Eric's about 5'8", I guess. And this is a pumice fall deposit. This is up near the top of Gibraltar Rock, for those of you who are familiar. The pumice fall deposits from Mount Rainier never really get much thicker than that. So Tephra is another word for volcanic ash. Sorry about all the technical words. Tephra really isn't much of a concern. In fact, this is a section through some tephras at the foot of Mount Rainier. This is my colleague Jim Valance with the Cascades Volcano Observatory. And you can see a number of light-colored layers in this, as well as some dark-colored layers. Each one of those layers that you see is a tephra or an ash deposit. But it turns out that the majority of the thick, really obvious ones, like this one here, and these here, and those there, are tephras from Mount St Helens. So Mount St Helens is very good at producing volcanic ash, as people who were living in eastern Washington in 1980 know. Mount Rainier is not. So tephras don't really concern us that much from Mount Rainier. Now, with the ongoing eruption or the recent eruption of Mount St Helens, you've heard a lot about lava domes. This isn't Mount St Helens. This is the recently formed lava dome at Mount St Augustine volcano in Alaska. Lava domes differ from lava flows in that they are much pastier and thicker, and instead of flowing down the hill like syrup, they just kind of build up in one place, and then from time to time they collapse. Mount St. Helens produces a lot of lava domes. It also produces, as I said before, tephra, and that has to do with the kind of magma that comes out of Mount St. Helens. It's a pasty, stiff magma, and the gases have difficulty getting out of it. There, in fact, is only one lava dome that we have been able to find at Mount Rainier. This is it. It's this low outcrop in the foreground, and you can see these upward curving bands. These are flow bands, and where lava domes have been eroded, so you can see their interiors, they commonly have a sort of a flower structure, sort of like a chrysanthemum of flow banding within them. And so there are lava domes at Mount Rainier, but they don't form very often because the kind of magma that comes out of Mount Rainier is much runnier. Lava flows and pyroclastic flows are the norm for the volcano. Well, so we do all this field work on Mount Rainier, and then we collect samples from the volcano and we take them back to the lab. We don't always collect ones that big, but as I said before, we then determine things like their chemical composition and the temperatures at which they're erupted, and particularly we are interested in their ages. And one of the things that falls out of our work on Mount Rainier, as well as other people's work on other volcanoes, similar volcanoes, is that the volcanoes grow in pulses. This plot shows eruption age, again, in kiloannum, or thousands of years ago, against cumulative volume. So, okay, so what does this mean? Each one of these symbols is the measured age of a particular lava flow, and then based on having mapped its outlines, I can determine what its volume was. And I just add them up, one after the next after the next. And then the colors simply represent different pulses of activity marked by inflections in this curve of growth against time. So the volcano that we call Mount Rainier started to form almost exactly 500,000 years ago. There was a little bit of volcanism earlier, and remember there was a predecessor or an ancestral volcano about 1 million years before, but the volcano we call Mount Rainier started 500,000 years ago, and since that time there is a continuous and a voluminous rock record of volcanism. Well, for the first roughly 80,000 years, the volcano was quite active. You can see it's very steep here. It added a lot of volume. And then for about 120,000 years, it throttled back. We don't really know why they alternate like this, but they do. And then again, there was about a 100,000-year period of heightened activity. And for the last roughly 180,000 years, the volcano has been throttled back again. So it's now nowhere near as active as it has been in the past. But you'll notice also what I show on here are what I call dike events. These are times when so much magma was moving through the volcano that it couldn't all come out of the top easily, and the volcano would split open, and magma would move out, filling cracks that it had created within the flanks of the volcano. Geologists' word for the hardened rock that has filled cracks like that is a dike. So during the times when the volcano was highly active, so much magma was coming through that it would split open and create these dikes. And these are important because they drive, and here's a photograph of one of these dikes. You see it's sort of a vertical blade coming up, cutting rocks, layered rocks on either side from the volcano. These are important because they've driven a process known as hydrothermal alteration. That's kind of a big word, or a big term. What hydrothermal alteration is, these dikes, when they come in, are hot. And there's a lot of groundwater in the adjacent rocks. And the magma that's filling up these dikes has a lot of sulfur in it. Well, so the hot magma that's filling the dike starts to act like a radiator. It heats the surrounding water, and that surrounding water starts to circulate. And at the same time, the sulfur is being given off by the dike. Well, the sulfur comes off as a gas, sulfur dioxide. Well, if sulfur dioxide dissolves in water, it creates sulfuric acid, H2SO4. And that hot, acidic water starts to attack the rock. And one of the things that it will do to it is it will convert it into clay. The clay, of course, as you all know, is soft, and that makes the portions of the volcano that have been altered susceptible to collapse. And when they collapse, instead of coming to rest as a big coherent debris avalanche, such as happened at Mount St Helens in 1980, the material liquefies, and it will flow down the river, or flow down the valley as a fast-moving slurry, or again, another type of lahar, with the distinction that the collapse-generated lahars at Mount Rainier tend to be voluminous, and they tend to be very far traveled. So dikes, they drive hydrothermal alteration, and we map out the distribution of the dikes. Those are shown by these little red lines. You can see that they're not everywhere around the volcano. They're concentrated in kind of a bow tie-like pattern. So there are some off on the northeast, and there's a lot of them off on the west. And then this heavy dashed line outlines the region that has been hydrothermally altered and weakened. And there's some complexities in this area that I'll get to in a moment. Now, you may have heard or read in the paper that hydrothermal alteration is ongoing at Mount Rainier, and that the volcano is stewing in its own juices, and it's getting progressively weaker in a kind of a scary fashion, like maybe it's not so bad now, but in 10 years it might be worse. Well, one of the things that we found actually is that as I showed you before, the alteration is associated with the diking events, and therefore it is also highly episodic. Most of the altered rocks that are present on Mount Rainier altered tens of thousands to more than 100,000 years ago. And this is some of the evidence that shows that. These brownish-hued rocks are hydrothermally altered, and the darker hued are fresher. And there are some ages on here. Just around the corner on the Mowich face, we have, and then more technical words, unconformity. That's an erosional break. So the rocks above this white and dashed line are younger than the rocks that are underneath it. And you'll see that they're not altered up here. Well, we have an age for this white band. This is a pumice band, and it's 195,000 years old. Just around the corner, we have another sample from above this erosional break, and it's 217,000 years old. And then just a little ways below it, we have a lava flow, again from around the corner, that's 277,000 years old. So that's probably very close to the age of these lava flows here. So these lava flows erupted, they were hydrothermally altered, erosion bit into them to make this crater, and then new lava, as well as some pumice, filled that in between about 280 and about 200,000 years. So the alteration that affected these rocks was done by the time those rocks came out. Now, there is alteration that's taking place at the summit of Mount Rainier, but we've done geophysical measurements on that, and it's no more than about 20 meters thick. So there is alteration on Mount Rainier, but it's fossil alteration. It's old alteration. It's still a hazard, but the hazard isn't increasing significantly within human lifespans. Okay, well, the eastern half of that bow tie of alteration fell off. It fell off 5,600 years ago, creating something that's known as the Osceola Mud Flow. The Osceola Mud Flow was full of clay, and it flowed great distances, and it left a horseshoe-shaped crater, much like the horseshoe-shaped crater that now exists at Mount St Helens and is slowly being filled in. This dashed line shows the perimeter on one side and the other of that horseshoe-shaped crater. But it's sort of hard to recognize because eruptions since 5,500 years ago have largely filled that crater in. And this smooth ice slope that you can see are glaciers that are mantling those younger volcanic rocks. And I think any of you can recognize the difference between the rugged topography here, the rugged topography over there, versus the very smooth topography that fills in that horseshoe-shaped crater. Now, the Osceola Mud Flow had a volume of about 4.5 cubic kilometers. To put that in perspective, the collapse at Mount St. Helens was about 2.25 to 2.5 cubic kilometers. So this was nearly twice as big. So this was a very major event, collapse of the eastern end of that bow tie of altered rocks that formerly traversed the volcano. These are some of the deposits from the Osceola Mud Flow. They have, again, that sort of brownish or tannish hue to them due to the alteration minerals. This stuff is full of clay. You know the Osceola Mud Flow whenever you walk on it because it starts sticking to your boots, and your boots start feeling very slippery underfoot. And this really is the nub of why I can get away with calling Mount Rainier America's most threatening volcano. So here are the glaciers. Here's the perimeter of the volcanic rocks from Mount Rainier. You can see the volcanic rocks, the lava flows themselves, really get nowhere near heavily populated areas. But this area in black is the region that has been swept by lahars, and the associated floods related to lahars from Mount Rainier in the last 6,000 years. Now, if you go through census data and count up how many people live in this black area, they're on the order of 150,000 people living on lahars and volcanic mud flow deposits from Ranier. Now, 5,500 years ago was a long time ago, but there were lahars that came out in this drainage that are as much as about 40 feet thick beneath the Puyallup Fairgrounds, about 2.5 to 2,000 years ago. So they went down here and down here. 1,000 years ago, lahars went down here and here. And then 500 years ago, lahars came out of the western flank, out of that altered area, and went down about as far as there. So it has continued since the Osceola Mud Flow event to produce lahars, and we have no indication, we have no reason to believe that it won't do that in the future. So this is the primary threat that Mount Rainier poses to residents of the Pacific Northwest. That you're not going to get run over by lava flows, but there is a good chance that a lahar will come down the valley. Well, as I said, since the collapse of 5,500 years ago, the volcano rebuilt its cone. This is a photograph of the summit. You can tell that this is recent volcanic construction because of the nearly perfect circular form of this summit crater. There was a slightly older summit crater there that's been bisected. If this was old, the glaciers would have had time to bite into it like they have on many other flanks of the volcano. For those of you who've been to the summit, you'll know that there's steaming taking place. There's a network of caves that are melted beneath the ice that's filling both of the summit craters. And there's even a lake. And one of the rangers of the park gives me his solemn assurance that in the 1970s, he carried scuba tanks up there, and somebody actually went scuba diving in one of those lakes. I can't verify that. Is that true? Do you think that actually happened? So we have independent confirmation that it's actually happened. Because of the heat that's coming out and is melting the base of these crater-filling snowfields, material that gets dropped in the summit crater very rapidly appears at the base. And so, for example, there are mittens, lunch. There's even an airplane that someone landed and then could not take off again, and it's melted through. And you can climb down into these. I haven't gone to look at it, but I have seen photographs of it. It really is there. There's an airplane. Okay, and then also looking up at that summit cone, for those of you who are familiar with glaciers, this will look funny to you. You see these raised ridges on the surface of the glacier? Glaciers don't normally look like that. The reason these raised ridges exist, as well as the larger ones here, for example, is that the ice is mantling young lava flows that came down from the summit. We've dated this outcrop here, and that's actually Camp Sherman there. Those are about 2,400 years old. And then we also have samples from the summit that are about 2,200 years old. So the youngest lava flows that have come out of Mount Rainier came out about 2,200 years ago. And this is a summary of what Mount Rainier has done in about the last 2,600 years. There's a lot of things on here. This is years before 1950. For technical scientific reasons, we use that as a reference point for things that we've dated by the carbon-14 method. And then there's a lot of colored circles here. Well, the red ones are ones where we have really strong evidence that magma came out of the volcano. And then the other colors, for example, there are historic accounts of an eruption in 1894. We have looked like dogs, but we can find no physical evidence for it. But the descriptions sound like a real eruption. So I think something probably actually did happen. So the most recent event at Mount Rainier was probably something very small in 1894. There was a large mud flow, as I said, about 500 years ago off the west side of Mount Rainier. We can't really find good evidence for new magma coming into the volcano at that time. We have tried. There's some suggestive evidence, but nothing that's really convincing. That's important because when new magma comes into a volcano, it gives us warning signs. There are more earthquakes underneath the volcano changes its shape, more gas of a different composition comes out. All of these things give us clues that something might be about to happen. For this event, this electron mud flow event, it really is unclear that any new magma came out of the volcano. So that potentially was an unheralded collapse event, something, the bump in the night, the thing that gives you no warning. The event that the most recent eruption that we can document was about 1,000 years ago, rather small, but created some quite extensive lahars down the White River Valley. And then about 1,600 years ago, again, producing lahars down the White River Valley. And then there was this period from about 2,200 to 2,600 years ago, when the volcano just erupted again and again and again for about 2,100 to 2,600. So about 500-year period when the volcano erupted again and again and again. So we have two sort of modes of behavior here. We have these isolated events, which are nevertheless significant. And then we have these times, sort of on a much smaller scale than the overall history of the volcano, when it erupts a lot. So these are the two things that we have to expect. And then there are protracted dormant periods. So from about 2,600 years ago to about 4,000 years ago, nothing was happening there. Well, so here are some of the deposits from that electron mud flow event. What this map in the upper right corner shows are areas of buried forests. And my colleague Pat Pringle from Washington DNR, Department of Natural Resources, has really homed in on these buried forests. What they are forests that were standing and then were partly buried by a lahar event. And this is a contractor, and he's putting in a housing development in the town of Ording. This is the town of Ording, and what he's done, I don't know what he's trying to do, put it in a basement perhaps, and he's uncovered this log. Well, this is a tree that was standing at the time the electron mud flow came out about 500 years ago, and it buried that tree plus all the others, and then the portion that wasn't buried, of course, rotted away. And the portion that was buried within the mud flow rots much more slowly, and so they're preserved. And Pat has found these in a number of areas, not just areas inundated by the electron mud flow, and has used them as yet another tool for dating when the volcano has produced lahars. And you can see how far these things go. I mean, this is the city of Seattle right here, and we've got some just to the south of the city. So this portion of the altered part of the volcano fell off about 5,600 years ago. This hatched line represents the perimeter of the collapsed amphitheater. This area with the crosses in it represents all the new lavas that's come out. But the altered rocks still remain on the west side of the volcano, and there are some highly altered rocks on the east side of the volcano, as well as this very thin skin of alteration up at the top. And one of the things we wanted to know was, how much more dangerous is this region of altered rock on the west side of the volcano? So another collaborator of mine, Mark Reed, who's a landslide specialist, has developed a computer model where he calculates millions. In this case, he ran 30 million potential failure surfaces through Mount Rainier and then calculated the relative stability of one failure surface versus another. And this incorporates the measured strength of the rocks. So a clay-rich rock will have a low strength, and a fresh volcanic rock will have a high strength. And he ended up with this result. This shows relative stability. Red numbers mean unstable, and cool numbers, so hot numbers mean unstable, and cool numbers mean stable. And then the degree of stability is about proportional to this scale. And the area that creates a bullseye in his model is that upper west flank, the region in which there is still a high concentration of altered rocks at high elevations. And we tried various other scenarios, such as putting altered rock underneath at great depth underneath the summit, and it really didn't change the overall calculated stability of the volcano. This is the kind of analysis that people do, for example, when they are engineering open pit mines. And they want to know how steep can they make the walls, and they very carefully map the geology of the walls and assign stabilities to it, and then actually calculate how steep can they make it, how high can they make the wall. This is pretty standard engineering geology techniques. And you can see that it does, in fact, highlight that upper west flank where the altered rocks remain in high concentration. Well, another aspect of Mount Rainier is that it's the second most seismically active volcano in the Cascades. Number one being Mount St. Helens, of course. Another colleague of mine, Seth Moran, did his PhD thesis at University of Washington with Steve Malone, studying earthquakes at Mount Rainier. And one of the questions that they had was, well, there's all this seismicity. Does this mean that the volcano is falling apart? Are we seeing earthquakes actually in the volcano representing its failure? So he studied these very carefully, put out a lot of new seismometers so he could very precisely locate the earthquakes. And what he found is that by far, the majority of earthquakes are taking place well underneath the volcano. They're not related to the volcano itself falling apart. Instead, they probably result from the deeper magmatic system. It's hot. There's a lot of steam and other volcanic gases that are moving up through and up out of the volcano, feeding the steam vents up at the summit. Where rocks are hot, they behave plastically or ductily. That's generally taken at about 400 degrees centigrade. Where they're cool, they behave brittly. So very probably, the earthquakes that are concentrated underneath Mount Rainier are manifestations of its hydrothermal system. The steam is moving through those rocks and facilitating their breaking. Say, for example, it could pressurize a zone so that fractures in that area can slip more readily than other areas. So the high concentration of earthquakes that's ongoing in a steady state way underneath Mount Rainier is a result of its hydrothermal system, not instability in the edifice itself. But if the abundance of earthquakes was to change, particularly if they were to increase in number or increase in and decrease in depth, that would be the kind of evidence that that would alert us that something new and different was happening at the volcano. But one of the problems that we've had at Mount Rainier, of course, is that it's a rugged place. It's also a wilderness area, so it's difficult to get instruments in there and keep them running. This is a map of Mount Rainier, and each one of these colored symbols is an area that's periodically surveyed for its position. And this is done to see if the volcano is swelling or shrinking, or see if one portion or another is moving, indicating that it might be slipping. But this, at least in the past, hasn't been done continuously. It's done every few years. And these are the locations of the existing seismometers at Mount Rainier, these colored symbols. And you'll notice two things. One is that there's not very many of them. And the other thing is that they're sort of in a line. And with a seismometer, one locates an earthquake by triangulation. So if all of your measuring instruments are in a line, you can't determine the location very well. So what we have done with a lot of collaboration with the National Park Service and lots of things like environmental assessments and permits and so on and so forth is to design some new long-term instrument locations. And these are coming in these locations here in the different color. We're putting in seismometer stations there. We're also adding continuous GPS, that's Global Positioning System, as well as adding GPS to the existing seismic sites so that we'll be able to see, particularly for this area here, which is in that altered zone, see as early as we can that the volcano might be beginning to fail. These are some of my colleagues putting in one of the GPSs last summer, Jim Valance, Rick Lehusen. This is largely a battery and instrument box. This is the Ranger hut at Camp Sherman. That's a solar outhouse in the background. This is what it looks like once it's been installed. That's Jim. This is the instrument box plus the batteries. This is the radio antenna that sends the data out continuously. That's the GPS antenna that's mounted on the top of the Ranger hut. This is another one that's been installed near Panhandle Gap. This Camp Sherman is not wilderness. This is designated wilderness. So this is in a place that is, in fact, difficult to see. You would have to look for this pretty hard if you walked around the Wonderland Trail. This is the GPS antenna. That's the instrument box. That big square there is a solar panel. This is the radio antenna. This installation is designed to radio down to the Crystal Mountains ski area, and from there tunnel into the intranet and provide the data continuously both to the University of Washington and to the Cascades Volcano Observatory. So what if we miss something though? Well, we have what you could call an insurance policy. These are what are called acoustic flow monitors, AFMs. They're like a seismometer. In other words, they're listening for vibrations in the ground, but they're listening for a different frequency range than an earthquake normally is manifest. They're listening in the frequency range that lahars have been found to produce. So for example, if a lahar comes off of this volcano and it moves down this river valley here, it'll shake the ground in a characteristic way. The sensor will detect that and then send a signal out by radio. This is a collaborative project with various county and state emergency services organizations. These people are installing one of the acoustic flow monitors on the west side of Mount Rainier. And they're arrayed in a pattern like this. The red triangles represent areas where the acoustic flow monitors have been installed. The way they're set up, because we don't want to have false alarms, is there are different tiers of these things in rows. So there might be, say, 3 or 4 down close to the river, and then 3 or 4 at a higher level, and 3 or 4 at a higher level still. And so to actually send a high alert that something is happening, they have to be triggered in sequence, going one to the next, down the river, and at least one of them has to be destroyed. That is, the signal has to actually be cut off because we don't want to have false alarms. So say a small event moving down one of these river valleys might trigger them in sequence, 1, 2, 3. But if it's not big enough to actually wipe one of them out, we don't want, for example, the town of Ording, which is down here, to be told to evacuate unnecessarily. Because if that happens, then the next time there's an event, which might be a real event, the public response will be much lower. So anyway, these things are installed in the rivers on the west side of Mount Rainier, particularly the river valley heading in this area of abundant hydrothermal alteration. The signals are radioed to Camp Murray and an emergency services center going by the acronym of LISA. If it's deemed by the people who are on 24-hour staff there to be a real event, if they really think that it's something going on, they then radio the information to towns like Ording. Those towns have warning sirens. The warning sirens go off. The people have been at least informed. Whether they've actually practiced or not is another thing, but they've been informed of emergency evacuation routes. The school children, however, and I live in California, so my daughter has earthquake response drills. Well, the children in the town of Ording have lahar response drills. So maybe once, maybe twice a year, the teachers get them up out of their classes and they line up and they've got an evacuation route out of the town. The important thing is not to say head down the valley away from the lahar, it's to head up the hillside. 50 feet above river level, 100 feet above river level can mean the difference between life and death. And I'm not exaggerating with that. There was a town in Colombia, Armero, in the 1990s, and a small lahar in Nevado del Ruiz swept down into that town, and it killed 20,000 people. And if those people had had some warning and had walked, say, 50 feet up the hillsides on either side, they would have lived. So this is a serious issue, and I have to say that the public response in the Puget Sound area has been overwhelmingly positive. And I think that's the case because of the 1980 eruption of Mount St Helens. If we had tried to tell people, absent the St Helens event, that their volcanoes could do something bad to them, they might not have believed us. But they are, and we're not actually asking very much of people. We're asking that say, their children have evacuation plans, or that when they're planning a new long-term facility, like where are they going to put a hospital, or how are they going to engineer a bridge, that they take this consideration into account. And as I say, the response has been overwhelmingly positive. So to sum up, hazards at Mount Rainier. Well, it's lahars, lahars, lahars. That's where the action is. So most of them form during times of unrest. That can sound like a bad thing, but it's actually a good thing because volcanic unrest gives us warnings, and that allows communities to implement the plans that they have formulated. Some of them form by collapse, possibly during these non-eruptive times, and then these times of eruptions can be brief, or they can span several hundred years. So imagine that. That would be a scenario in which Mount Rainier is producing a major lahar, say every 50 years or every 100 years. This would be something that people, of course, would have to adapt to. How are we responding to it? New and more instruments to better locate the earthquakes and detect early slope failure. That's in reference to this possibility that some of them could collapse without warning. We've got a backup system, sort of an insurance policy of the acoustic flow monitors in the most hazardous valleys with an automated warning built into that. The communities have developed evacuation routes. Volcano hazards has been incorporated into the curriculum in the elementary schools, just like earthquake hazards are incorporated in the curriculum in the elementary schools down in California. And then we pointy-headed scientists do various kinds of research on volcanic and mass wasting processes so that we can improve our ability to predict what's going to happen. And that's it. Thank you.